Hello, everyone, and welcome to our live session. My apologies for getting started a little late. We are having some technical difficulties, but we are here and we are ready for your questions. Welcome. This is your first time with us, we are happy to have you here. If you've been with us for a long time, welcome back. We hope that you enjoy this new year, and we hope that we can start you out with some fantastic and interesting astronomy, astrobiology, history, and philosophy information. My name is Matthew. I'm sort of behind the scenes instructional staff. Chris, I'm going to hand it over to you just to welcome everyone, and then we'll get started right away with questions.
Okay, welcome everyone, however you encountered us, online courses or just have been here before. The floor is open for any question about astronomy.
Excellent. So the way this works, for those of you who are new with us, post your questions in the chat. I will grab them from there. We try to get a variety of topics and questions. We generally go in order, but I jump around a little bit to try and get a variety of topics and give everyone a chance to ask questions. The first question is going to be from Ragnar Lodbrok, who asks, escape velocity from Earth is 18 kilometers per hour. If Earth spun as fast as Saturn at 22 kilometers per hour, would all of the trees, cows, and people fly off of the Earth?
I think that number in the question is wrong, 12 kilometers per hour. I think it's per second. So if we just assume both your numbers are per second, not per hour, because 12 kilometers per hour is actually pretty slow. I could almost run that fast. So if that's the escape velocity, yes. And so in principle, if a planetary surface is moving at the escape velocity for that planet, in terms of its rotational speed at the surface, then yes, the centrifugal force would counter that of gravity and objects would fly off the surface. But that turns out to be an incredibly fast speed, so no planet ever rotates at anything like that force. And so the centrifugal force of objects on a surface of a planet, any planet in the solar system, is tiny compared to the gravitational force that keeps objects tethered to the surface.
Excellent. The next question is from Lawrence K. Hi, Professor. Is Hawking radiation generally accepted in the scientific community, and do black holes really evaporate?
Hawking radiation is obviously a prediction of Stephen Hawking, who's no longer with us, but it was one of his foundational contributions to black hole theory in the 1970s. It is a theoretical prediction that has never been observationally confirmed, and in fact would be extremely difficult to confirm because it's such a subtle signal that in terms of temperature it amounts to billionths of a Kelvin. Astronomers simply have no way of measuring that tiny temperature, which is also corresponding to a very slow evaporation rate, so they can't measure that either. It's generally accepted because the theory he produced was very robust, and people have worked with his theory and his formalism for half a century now, and nobody's found any serious errors with it. So it seems like Hawking radiation should be a real phenomenon in the universe, but we simply haven't measured it yet, and it may never actually.
The next question is from Parth Agarwal, who asks, is time travel possible?
Not as far as we can tell. The laws of physics do not allow time travel because the laws of physics are grounded on causality. It's also a foundational principle of science itself. Causality just essentially says that events have causes that can be identified. And so there are events and they have causes that you can identify that preceded them. And that ordering is important because if events happened with no identifiable causes or in the reverse order, then it would be a chaotic universe. So the implication of time travel is really to deconstruct physics as we understand it, or the logical, normal, sensible world as we understand it. That's not to say that it could not happen, it's just that current theories argue strongly against time travel.
Excellent, thank you very much. The next question, excuse me, is one from one of our live participants. Lalita Sharma asks, I was wondering, at the start of the course, it says the sun was created as a consequence of different cloud densities, but what causes it? Why is the cloud not equally spread out?
Well, the medium between stars, the interstellar medium, is a diffuse medium. It's very low density, about 1 particle per cubic centimeter, compared to the air you're breathing, which is a billion particles per cubic centimeter, so almost perfect vacuum. But it's not entirely uniform or smooth. Gravitation causes clustering of that gas and clumping of the gas, and stars within it exert pressure, radiation pressure on the gas, which moves it around. So the gas is never uniform. It's a chaotic, turbulent medium stirred up by stars, formed into clumps by gravity, and that's why wherever the position of the sun was when it formed was probably an overdensity of a much larger cloud of gas.
The next question is, so that also covered a question by Kaniz Fatima, who asked something very similar. But the next question from Kaniz Fatima is, why is the moon drifting away from us?
The moon is drifting away from us very slowly. I think the number is about 4 centimeters per year, just an unimaginably small amount, but it is actually measured because we've left reflectors on the moon since the Apollo era, so we can do laser ranging of the moon very accurately and know its distance. The reason why it's happening is because of the gravitational coupling between the moon and the Earth. The Earth obviously keeps the moon in an orbit around it, but there's an interaction in both directions because Newton's gravity says the force that the moon exerts on the Earth is equal to the force that the Earth exerts on the moon. And that gravitational coupling actually transfers angular momentum. So conservation of energy and angular momentum state that as the moon moves slowly away, its hold on the Earth causes the Earth to very slowly spin down. And so the Earth's year is getting very slightly longer as the moon moves slightly away. And those two effects balance out, and so the conservation of energy and angular momentum are preserved through that interaction.
Excellent. Thank you very much. The next question is from David Gold, who asks, what caused volcanic activity to stop occurring on the moon so many years ago?
That's an interesting question. The moon is geologically dead, and yet it has volcanoes. So that's an interesting phenomenon because the moon is quite low mass. It's a very low mass object. And tectonic activity or volcanism is usually only associated with massive objects. Now the moon does have an extra phenomenon that helps cause volcanism, which is the tidal effect of the Earth. So it's in a slightly elliptical orbit with the Earth, and the gravitational squeezing caused by the Earth gives some interior heating to the moon. The rest of the heating comes from radioactive decay within the moon rock. And when the moon first formed and was a semi-molten or magma interior, there was able to be volcanism then during that short period of time. But eventually, when the moon's whole mass cooled, that volcanism ceased, and there's simply not enough energy being produced within the moon to reinitiate volcanic activity.
The next question is from one of our live participants. I've not heard of this discovery that they're talking about, so if you have, that would be great. If not, then we can move along. So the Psycho Messiah asks, what is the significance of the new Big Ring discovery? How can galaxies align themselves in an almost perfect circle 1.2 billion light years across?
So this ring signal is still being debated. It's a pretty recent discovery. There's no easy mechanism for explaining how galaxies will align that way. Gravity is the only real force that causes galaxies to arrange themselves in a particular pattern, and that would not actually produce a ring pattern. What this signal may be, however, is a signature of acoustic oscillation. So low-density plasma in the early universe had waves with very long wavelength, and those low-density plasma waves of the early universe, as the universe expanded, the waves get very long, and they could, in principle, imprint patterns on large-scale structure on very large scales. So that's a potential mechanism for this ring, but basically it's a brand new result and still being investigated.
Excellent, and that also was asked by Donald Spicer, so thank you very much for those similar questions. It's always great when we can address some recent discoveries. The next question is from, let's see, from R. Moser, who has a specific question about AI tools, but can you just talk a little bit about, in general, how we use artificial intelligence tools in the analysis of astronomy data?
Sure. Astronomy has used AI methods not just recently, since AI has been in the news a lot the last few years, but AI has been used in astronomy for decades, actually, because astronomy is always dealing with big data. There are large data sets, huge surveys, surveys of the sky involving hundreds of millions of objects and trillions of pixels of data, and analyzing that is extremely difficult, and it cannot be done by hand. And so looking for the subtle patterns that constitute the behavior, interesting behavior of objects, or just detecting objects themselves, is best done with the help of AI. And so all big surveys now use AI methods to help them with their detection, because humans simply couldn't keep up. And so that's been true for the past few decades, and now is increasingly true. AI is also being used to make discoveries, because AI is actually good at looking for unanticipated signals, or things that aren't the normal category of objects. And so looking for anomalies is something that AI has proven to be very good at.
The next question is from Lalita Sharma. In the lecture, one of the classes, it says that our sun is actually spinning around a point just outside the sun. So does that mean that we orbit, or that the Earth's orbit around the sun of 365 days is not accurate?
This is a very small effect. So the fact that the sun essentially pivots around a point at its edge rather than just spinning around its center is caused almost entirely by Jupiter. Jupiter is the largest planet in the solar system, the most massive, and it exerts a tugging force on the sun, and that leads to what's called a reflex motion. So the reflex motion is this pivoting of the sun as Jupiter goes around it, tugged by Jupiter. This doesn't really affect the Earth on an interior orbit, because remember, the amount that the sun is being moved is just a half of the sun's diameter. So it's a few 100,000 kilometers. And the Earth is 150 million kilometers from the sun, so that it has a negligible effect on the Earth's orbit.
The next question is from Chamila, who asks, there is something called time dilation, right? So how do we measure the age of the universe if time isn't the same for everywhere in the universe?
Well, we measure the age of the universe because our cosmological model involves the expansion of space-time, and that expansion model incorporates time dilation. So it's built into the model, essentially. And so you have to calculate, using the expanding universe model, expanding space-time and time dilation as part of it, what the age of the universe is. So it's not a simple calculation, because you're actually using the cosmological model, which involves general relativity.
The next question is from Campbell, who asks, piggybacking on that question, how concrete is the age of the universe?
The age of the universe is not a very precise number. In cosmology, some numbers are measured more accurately. I would say the age of the universe, which is quoted as about 13.8 billion years, is accurate to better than 10%, maybe 5%. It'll be hard to get it closer to 2 or 3%. That would take a lot of work, because in the end, the age is built into a cosmological model. It's based on tracing the expansion history of the Big Bang back to the origin, given the current conditions, current amounts of normal matter, and dark energy. And there are uncertainties in those constituents of the universe which project into an uncertainty in the age in the Big Bang model. So measuring a more accurate age would require more accurate measurement of the constituents of the universe that we see around us.
The next question is from David Goldmeyer, who asks, does the James Webb telescope have to make position adjustments to stay in the Lagrange position?
Yes, it does. The Lagrange point place location where the James Webb is situated is what's called an unstable equilibrium. In other words, if unattended, the James Webb Space Telescope would drift very slowly away from this in this unstable equilibrium. It's a gravity balance point, but it's an unstable one, where if you move away from it, you will gradually move further and further away. The James Webb Space Telescope has small thrusters or jets or retros, rockets, which enable it to keep in rough position very easily with a very low fuel cost. So the ability to stay in that position using small thrusters is by no means limiting the timeline of this telescope. It has plenty of fuel to do that for decades.
The next question is from Norman, who asks, did you see the news article that the small Magellanic Cloud might actually be two dwarf galaxies instead of one? Can you talk about how we find something like that out?
Yes, this is a recent research result. It's now resulted in a publication and made news stories. The Magellanic Clouds are likely not to be single objects. They're composites, and that's because the dwarf galaxies that surround the Milky Way, of which Magellanic Clouds are just the two nearest examples, they're just two members of several dozen dwarf galaxies, and these dwarf galaxies sometimes collide and merge. And so it's not unusual in the environment of a big, massive galaxy that some of the dwarf companions around it interact or merge. And that seems to have happened with Magellanic Clouds. The way we know they're not single objects is we actually measure spectra of individual stars in the Magellanic Clouds. And we can see by their velocities, their radial velocities, and even their proper motions and their chemical composition, that they're not a single homogeneous population. And so it looks like you can see two objects in the properties of the stars.
The next question is from Kaniz Fatima, who asks, why is there a prediction of a solar storm in 2024? Will it cause destruction or damage to Earth somehow?
It's just consistent with the way the solar cycle works. We're heading towards an apex. We're heading towards an inflection point in the solar cycle, and that's typically a time when there are solar storms. Predicting the actual strength of solar storms is very difficult because there are, for instance, superstorms on stars like the Sun that happen every few hundred years or millennia. They're extremely difficult to reliably predict. So I would say this is a slightly generic prediction, just associated with where we are in the solar cycle.
Excellent. The next question is from Liddy, who asks, can you talk a little bit more about Fermi's paradox? What is it, and what is your take on the Fermi paradox?
So Fermi paradox was posed by Enrico Fermi, the famous physicist of the 20th century, who was responsible for the first sustained fission reactor and reaction at the University of Chicago, where he spent most of his career. He's a preeminent physicist of the 20th century, and he was thoughtful enough to realize that even though it was decades before exoplanets would be discovered in the mid-1990s, back in the 50s, he recognized that the likelihood of life in the universe was quite high, that the ingredients for life were there were likely to be planets around other stars, and plenty of time for interesting things to happen and life to evolve. And putting the numbers together in a simple way, he realized that it might be unusual for us to be alone as an intelligent, advanced civilization. And so he inverted the question, are we alone, into where is everyone? And the Fermi paradox, as it's phrased, is the incongruity between the expectation that there are a lot of intelligent civilizations out there and the fact that we haven't made contact. Now, philosophers sometimes will argue that it's not formally a paradox, which are two mutually inconsistent statements. This is not a paradox because we don't have evidence to talk about whether there's life in the universe at all. So that's why it's not actually a paradox. And so sometimes it's just left as the Fermi question, where is everyone? And it's a well-posed question now as it was 75 years ago. And there are many possible answers to Fermi's question. They might not exist. Intelligent life may be very rare. They may not last very long. The distance to the nearest civilization may be extremely large, so we're isolated in time and space. They might not be interested in making contact with us. They might be so advanced as to be unrecognizable, and there are many other possible answers to the question or the paradox.
And then a follow-up to that is, do you have any ideas or suggestions for books or articles or institutes to follow if they have further interest in the Fermi Paradox?
The SETI Institute has a web page. It's at least one and maybe several web pages on the Fermi Paradox. There's also a book written, it's probably 10 or 12 years ago now, but the information hasn't really changed since then because we haven't found life anywhere else in the universe. I think the book is called Where's Everyone? It's by Stephen Webb, and he poses actually something like 50 potential answers to Fermi's question. So that's a pretty nice summary, and most of those that he proposes are still valid now.
The next question is from Katrina. I'm interested to know whether the 2021 Pentagon report on unidentified aerial phenomena changed your thinking at all about astronomy and future discoveries, or what your thoughts are on that report.
The Pentagon report on UAPs, or unidentified aerial phenomena, as the military has rebranded UFOs, I did read it, and it's interesting. It was equivocal about the nature of UFOs because so many of them have no easy explanation, but over half could be readily identified with atmospheric phenomena, with weather balloons, with astronomical objects like Venus. So at least half of them had a simple explanation. And for many of the rest, there simply wasn't enough data or good enough information to draw a conclusion, and so they did not draw a conclusion. They also said very firmly at the end of the report that there was no actual evidence that any UAP was an extraterrestrial visitation by an alien civilization. So they did not give fuel in that report to the standard trope of UFOs as aliens visiting us.
The next question is an email from Ravi. Gravitational waves are ripples in space-time, but we usually talk about their spatial effects, like how they change the length of LIGO's arms. Is there a corresponding effect in the time dimension, either as far out as we can read, that they reach us, or maybe closer up, where all of that energy is first deposited?
There is the primary effect of gravitational waves is a displacement, just a physical displacement of space-time. There is a secondary effect, though, because a gravitational wave is a local compression of amplitude of gravity. So gravity is slightly stronger in the peaks and slightly weaker in the troughs of a gravitational wave. And since we know that time is based on local gravity according to general relativity, in principle time operates slightly differently through a gravitational wave, or it does flex time in a very small amount, and that's not anything that's been measured directly. But in principle, general relativity says there should be some very slight modulation of time caused by gravitational waves.
Excellent. The next question is from one of our live participants. Pecornin asks, when two black holes merge, they lose energy. Doesn't that contradict the idea that nothing can escape a black hole?
Well, nothing can escape from within the event horizon, but the black holes also have other properties. They have gravitational energy, potential energy, and so when two black holes are in orbit around each other and then merge, they are transferring gravitational potential energy into kinetic energy of their increased motion, and that can translate into accelerating gas near the event horizon and causing radiation to flow and so on. So the conservation of energy in the black hole in spiral leads to observable effects that happen outside the event horizon.
The next question is from Kelly. Why is the sun's outer atmosphere hotter than the chromosphere?
It's an interesting puzzle in physics. It was viewed as a puzzle for over half a century. Eugene Parker was a famous stellar theorist or solar theorist out of the University of Chicago, and he put out the best ideas at the time, back in the 60s and 70s, of how magnetic reconnection energy, when magnetic fields reconnect in the sun, because it's a very active object with sunspots coming and going, and the threaded magnetic fields in those sunspots and prominences reconnect and connect, that imputes electromagnetic energy out, which travels out and can heat a very diffuse plasma to very high temperatures. So the corona of the sun has a temperature of about 2 million Kelvin, and it's extremely diffuse, low density, and it is, of course, much hotter than the chromosphere. And that's the reason that is supposed for that is the transmission of electromagnetic energy from magnetic field reconnection in the surface of the sun.
The next question is from Chamila, who asks, I saw an article that said there could be a Dyson sphere around a star called Tabby's star. Can you talk a little bit about the observations that might lead to something like that, and what the current thinking is?
Yeah, Tabby's star is a star that several years ago was hypothesized as potentially showing evidence for an alien civilization, because it's the variations in the brightness of Tabby's star were quite dramatic and rapid, and didn't seem to be normally explained in terms of the types of variable stars we know about. There are dozens of types of variable stars, but Tabby's star didn't fit that. Now, since then, it's become likely that what's going on in Tabby's star is that it's surrounded by a debris disk, and some parts of the debris disk are very dense. And as that debris disk orbits the star, it occults the star and lowers its brightness significantly, and then rises quickly because it's on a rotation time period. So I think we understand what Tabby's star is doing, and it's got nothing to do with aliens. The speculation, however, was that an advanced civilization would build what's called a Dyson sphere, named after Freeman Dyson, famous Princeton physicist. It's a structure built close to a star, around a star, to capture the entirety of the solar radiation, whereas the Earth intercepts about a billionth of the sun's light, and we use a small fraction of that. This would be a way for a civilization to harness essentially all the energy of a star. Now, it's not a spherical object, it's not a solid sphere, if you like, around the star, because the stresses, the differential rotation of that would lead it to break it apart. So it's going to be a loose trellis type structure with solar collection as part of it. But we don't have to reach for that explanation with Tabby's star. The more conventional explanation will work.
The next question is from Hernan Reyes, who sent an email. It's, I am 72 and in good health. What are the chances I'll live long enough to get information on Life 2.0, one way or the other, from something like the Europa Clipper or Dragonfly missions? Do you think those are going to happen in the next 10, 15, 20 years? What's the timeline and likelihood?
Sure. I mean, I'm getting close to 70 myself, so if you're around that age, my suggestion obviously is to exercise and eat well to make sure you live till 90 or beyond, because I think that will be required. These outer solar system missions to look for Life 2.0 in the outer solar system of Titan or Enceladus or Europa, they have been historically very expensive, difficult to get funded, difficult to get on the manifest for NASA, because NASA does focus a lot on Mars. And so I don't think any of those three targets are going to receive a visit within the next decade. It's going to be into the mid-2030s before information might come back from any of those missions based on current timelines. And of course, budgets are very uncertain that far ahead, based on the election cycle in the US messes up everything. But yes, I think you should be, by your mid-80s, you should be getting information about Life 2.0.
The next question is from Irina. How well have we examined the moon's surface and topography? Is there anything that might still surprise us?
The moon is a pretty heavily studied object at this point. I mean, apart from the moon landings themselves, which returned 460 or so kilos of moon rocks that we are still learning things from, We've had the Lunar Reconnaissance Orbiter. That was a very impressive orbiter that could image the surface down to the size of rocks that were they'd be as big as your fist, so very small features. We've had magnetic imaging of the moon. We've had imaging that will be sensitive to water and frozen liquids under the surface, because we're interested in where the frozen water is. So the moon is a pretty heavily studied object at this point, and I doubt there are any major surprises.
The next question is from Adrian, who asks, Professor Impey, can you talk about the physics that causes the iron core of a star going supernova turning into a neutron star? How does a process like that happen?
In the advanced evolutionary state of a massive star, iron is viewed as sort of the end of the road for stellar fusion, because the binding energy per nucleon is at a minimum for iron in the periodic table, which means it's the most stable element. And what that means is you no longer get energy out by compressing or trying to fuse iron. And so that's where stellar fusion runs out. And so it stops there. Previously, up to iron, you're able to get energy out by fusion just by increasing the temperature and density and pressure. So iron is where it stops. And then eventually, when there's no more support for the star, there's no more fusion because all the heavier elements have been made, then gravity must take over and the star must collapse. And so it's the collapsing core of a star that's exhausted its fusion at the point of creating iron that leads to a rebound, a blast wave, a supernova. So the compression creates a neutron star or black hole, and then the bounce that leads to a blast wave is what causes the creation of heavy elements in the supernova glowing remnant that expands out into space.
Thank you. The next question is from Campbell, who's on with us live. Was all matter more dense than hydrogen created within stars?
Hydrogen and helium and lithium and deuterium are the elements, the light elements that were made in the Big Bang. So they were made in the very early universe, when the whole universe was the density and temperature of the sun, the core of the sun now. All the elements beyond those light elements were indeed made inside stars in subsequent generations of stellar evolution.
Stargazer's Kingdom, who's on with us live, asks, can you provide more context about the most distant fast radio burst observed by Hubble in 2022? What does the recent finding of its origin indicate?
The fast radio burst phenomenon is still a little enigmatic, but it seems to be associated with the creation of black holes and their ability to accelerate material. But there are several different astrophysical models for how you get a fast radio burst, and so we don't really uniquely understand them. This particular fast radio burst was extraordinary because the strength of the signal was so good that it could be observed in many different radio observatories.
The next question is from Kelly. Can time be stopped using some kind of quantum mechanism?
That's an interesting question. Time in principle stops at one place in the universe, and that's at the event horizon of a black hole. So if you look at the time dilation at general relativity, as you reach the place in a gravity situation where you have an event horizon, then time halts completely. So that's the place where, according to current physics, general relativity, we think time actually stops. Now in quantum world, we haven't actually stopped time necessarily. There have been very powerful trapping techniques that have been used to trap individual atoms, and that's an extraordinary technique. But time still flows for those atoms. So I hadn't heard of any way that time is frozen in a quantum arena.
The next question is from Chamila, who asks, is there any such thing as a white hole?
White hole's speculative, potentially the flip side of a black hole, so a place where energy is coming out, perhaps because of a a connection between two different points in space-time. So it's a theoretical construct that is in general relativity as a possibility, but there's literally no evidence for a white hole. And it would actually be very surprising if white holes exist, because space-time in the general universe seems to be quite flat. And so we don't seem to see any of these interconnected regions that would lead you to have a black hole, white hole pair.
Aditya asks, what are the roles that geologists play in the field of astronomy or exobiology?
Geologists are very important in the interdisciplinary subject, particularly of planetary science and astrobiology. So planetary science now deals with the very detailed properties of the planets in the solar system. And so geologists have been heavily involved in understanding how the planets in the solar system work, or the smaller objects, the comets, asteroids, meteors, and so on. And now that we know more about exoplanets, geologists are involved in that field too, because we know enough about exoplanets beyond just their mass and their size to try and understand whether they are geologically active or tectonic, whether they have mountain ranges or continents. At the moment, it's just predictive. We don't have a lot of measurements of the geology of exoplanets, but that discipline is really important in understanding them.
The next question is from Sium, who would like to stop interacting with the Higgs field and wants to know how one can do something like that.
I think you've got no real play there, because the Higgs field, if as understood, is what ascribes mass to all fundamental particles, and in the sense that it's how we get mass. I mean, a human being is made of atoms, quarks, electrons, neutrons, protons, etc., and the Higgs field is what generates mass for those. So to excerpt yourself from the Higgs field would be to deconstruct the idea of mass entirely, and perhaps have no mass, and I don't think that's physically possible.
The next question is from David McKenzie, who sent an email. What areas in the field of astronomy can an amateur astronomer make the most contributions to the field?
With the current equipment amateur astronomers have access to, which is, telescopes a significant fraction of a meter in size or collecting area, and high quality CCDs, the areas where amateurs make the biggest impact are in work on exoplanets, where sometimes just detailed monitoring is required. Not all exoplanets are very faint. You can observe transits of exoplanets around bright stars with a small telescope. So exoplanet research is an area where sometimes just a lot of data is needed and a lot of eyes on particular objects, or synoptic or continuous monitoring of something for days or weeks or months. Another area is the detection or search for supernovae. So we're still looking for the supernovae that go off in large galaxies, typically in each large galaxy about one per century, but if you're observing hundreds of galaxies, then there should be one going off pretty much every year in one of them, and small telescopes are very good at seeing that. Variable stars is probably a third area where small telescopes and amateurs can play a big role, because again, it's about a detailed monitoring of objects that are stars that may not be that faint.
The next question is from Stargazer's Kingdom. They'd like to know, what is baryonic matter?
Baryonic matter is the stuff we're made of, essentially, humans and the Earth and all stars. It is protons, neutrons, and electrons, essentially, and this related smaller number of particles that exist there. So baryon means heavy particles. So baryons are typically protons and neutrons, and that's the bulk of normal matter.
Excellent. The next question is from one of our live participants, Marie. Is it possible that we have found life on another planet already, but are simply not able to detect that it's alive because it's completely different to what we know now?
It's entirely possible. So it's a good question, because astronomers, astrobiologists worry about this. They worry about the fact that if we look too specifically for life as we understand it and know it on the Earth, we may easily miss life that's different from that. So it's a tension in the field, because you have to look for something, and obviously, since we are the only living planet that we know of so far, so it makes sense to look for the kind of biology that the Earth produced. But it should not lead anyone to assume that there couldn't be forms of life that are unusual or strange. And then the problem of detection is really difficult, because how do you define an experiment to look for something when you don't know what that something is?
Campbell, who is on with us live, would like to know, if extraterrestrial life existed, how likely is it that they would be carbon-based? So kind of related to that previous question.
Most chemists and biologists and astronomers do think that carbon-based chemistry and biochemistry is going to be how life in the universe operates in general. And that's because carbon is essentially unparalleled as an atom, as a structure for coding complexity and building long chain molecules. With carbon and hydrogen, hydrocarbons, you can essentially build an atom of infinite length and size and complexity. The bonds that carbon forms are quite stable, and so carbon chemistry is a very good basis for biology, since the biomolecules are trying to do reactions and build structures that sustain, and then in the end they're wanting to code information. Silicon sits in the same column of the periodic table as carbon, so it has similar electronic properties, but it's not as good at making long chains or stable molecules. So although science fiction likes to talk about silicon-based life, most chemists think it's not a good option, that it's unlikely to happen. And so carbon-based life seems to be the way the universe would work.
The next question is from Tani. There are kind of two ways to interpret this question, so maybe we can talk about both of those. Is there any estimation of when our solar system will complete one revolution around its center? So there's the revolution of the solar system, but also our solar system is moving around the galaxy. So they might mean, how long does that take?
Right. So the solar system has a series of orbits, and the outermost planets take something like a century to go around. So the solar system does a full orbit in roughly a century. The orbit of the movement of the solar system as a whole around the galaxy, the disk of the galaxy, is an entirely different matter, because the galaxy is, we are 27,000 light years from this galactic center. So 2 pi times that, or 6 times 27, you can see that the sun and the Earth and all the planets are going around the galaxy on a very long timeline of hundreds of thousands of light years. And that takes about a quarter of a billion years, 230 million years, I think. So that's the orbital time of the solar system around the center of our galaxy, which is interesting, because it means that since the Earth formed, we've done a couple of dozen orbits of the entire galaxy.
The next question is from Space to Space. Is the Big Bang Theory sufficient to describe all about the beginning of the universe, or is there still something that's missing or unexplained?
The Big Bang is doing a good job, as we speak, of explaining the properties of the universe we see, the microwave background, the expansion of space-time, and the fact that things were hotter and denser in the past, also the age of the universe at about 13.8 billion years. But it by no means explains everything. The Big Bang it takes as ingredients the two biggest components of the universe, dark energy and dark matter. But the Big Bang does not explain what those are, and those are still two profound mysteries in astronomy. The Big Bang also doesn't explain what caused it or what came before, and they may not even be meaningful questions for science to ask and answer. But it doesn't have all the answers. And then when you go back to the very origin, you're dealing with incomplete physics, because we don't yet have a theory of everything, if you like, a theory that unites the four fundamental forces. And we believe at the origin of the universe, those forces were unified. So we don't have a theory to explain that or talk about that. So there are some holes or some limitations of the Big Bang Theory, but within its realm of testing and prediction, it's performed extremely well.
The next question is from Sarah, who sent an email. I would like to ask your thoughts about the Antikythera mechanism. Can you talk a little bit about what it is? And do you have any recommendations for other objects similar to that might be interesting to research or learn about?
The Antira Mechanism is an extraordinary object. It's a historical artifact. It's essentially an analog computer from around 2,000 years ago. It was discovered in a shipwreck in the Mediterranean about 100 years ago, but the ship went down 2,000 years ago. It's easy to say from radioactive dating how old this artifact was. And in the hold of this ship and on the sea floor was this a pitted and corroded and almost unrecognizable object that was brought up to the surface by divers. And then a very painstaking research project that took 15 years, I think, to take what was left of this object, because not every piece of it survived, peel it apart layer by layer under controlled conditions, and then project what it really looked like when it was fully fledged and fresh. And what it seemed it was a analog computer and a sort of calendar system, a way of predicting the eclipses, a way of tracking the motions of the planets in the solar system. It was built from, I think, 57 different gears. They're eccentric gears because they accounted for the elliptical orbits of the planets, which weren't supposed to be known until Kepler's time. So it was an extraordinary device containing an enormous amount of information. It was probably being carried as a demonstration device on a trip around the Aegean for the Greeks to impress people as to their mastery of these kind of tools. It's possibly based on a design by Archimedes, but we don't really know that for sure. And at the moment, it's a unique object, so there are no other comparable objects. But in history, when you find something unique, it's dangerous to assume it's the only one, because the survival of these things after thousands of years is pretty difficult.
The next question is from Kelly. Why is our galaxy flat? Is it because of the space and time description you were talking about earlier?
Well, our galaxy is flat because it's a spiral galaxy, and it actually does have a component that's not flat. So the galaxy has a disk component, which we occupy, and we go in an orbit around the disk every 250 million years. And the disk was flat because this quasi-spherical or nearly spherical gas cloud had a small amount of rotation. And so the collapse occurred preferentially down the axis of rotation, and that leads naturally to the formation of a spinning disk. And then the stars form out of that spinning disk, and so you have the sun and all the other stars. So that's the flat component. Meanwhile, there was a preceding or a primordial component called the halo, where stars formed in the very early in the collapse phase, condensing out of the diffuse gas in the halo. The halo has a very small amount of rotation. It's not completely spherical, it'll be slightly aspherical, but it's a generally nearly spherical component of the galaxy, and the galaxy has these two components, as does every spiral galaxy in the universe.
Excellent. The next question is from Nia, who asks, what is the difference between the fields of astronomy and astrophysics?
They are very closely related, and some PhD programs, for example, in the US, call the PhD Astronomy and Astrophysics. You have PhDs in astronomy and PhDs in astrophysics. So in the professional world of departments of astronomy and PhDs and so on, those two words are mixed. Astronomy is a historical term that probably came first, which refers to studies of all the objects in the universe, their positions, their movement in the sky, their physical nature, and so on. So it's really based on observing. It's a sort of observational-based idea of the science of astronomy, what's in the universe and what can we see and how do we measure it. Astrophysics is more about how things operate. It's the physics of things in the universe and how they behave. So how do stars shine, and what's the gravity theory that predicts the clustering of the universe, and so on. So they're not inconsistent. I mean, there are complementary designations of the field, and that's why sometimes people join them together and call it astronomy and astrophysics.
The next question is from Lolita, who asks, is it worth studying exoplanets since they are thousands of light years away? So what if we find life out there, we can never reach it?
It's true that exoplanets are far away. I mean, the nearest planets are dozens of light years away. But there are some very interesting exoplanets that are quite close. Alpha Proxima Centauri b is a probably Earth-massed planet around the very nearest star to the Sun, a red dwarf, and it's quite possibly habitable. So there's a planet, an exoplanet that's as close as it could possibly be because it's around the nearest star, just over 4 light years away. And there are other exoplanets that are within a few dozen light years that are Earth-like or potentially habitable. So while most exoplanets, especially those found by Kepler, are indeed hundreds or thousands of light years away, there are plenty that are very interesting for follow-up study that are quite close. Maybe not close enough to visit, but certainly close enough to get really good information.
All right, it is 11 o'clock. This is going to be our last question for today. Joe B1188, who's on with us live, would like to know, I don't have a telescope, and I live in an area where light pollution is really bad, but I am a programmer. What kinds of contributions can I make as an amateur astronomer to the field of astronomy?
Well, if it's hard for you to do actual observing because of your light conditions, but you're a programmer and good with code, there are definitely ways you can contribute. You can work with amateur astronomer groups. There are networks of amateur astronomers that share data, and many amateur astronomers are good with the equipment and good with the observing gear, and they're not really good with computers or data reduction. So you can probably get involved in some citizen science projects or some consortia of amateur astronomers who are maybe observing exoplanets or variable stars or looking for supernovae, where your coding skills could really help them in data reduction and perhaps even in detection of interesting objects in their data. That's what I would suggest. Thanks for all the questions. Good set today, and I think we have another one on the schedule, but I don't remember when it is, but we'll be back with you in a couple of weeks.
Yes, that's true. We have another one in 2 weeks. I've forgotten the exact date. It's in the email for our classes, but just check our upcoming live streams or subscribe to the channel. That'll even be a better way. But it's in 2 weeks in February, and we are looking forward to seeing you all then. And we hope that you have a great rest of your week, and take care, everyone.